Welcome to our first chapter on statistics. I know what many of you might be thinking. Statistics can seem intimidating, but I want you to know that statistics is actually something you already use every day, even if you don't realize it. Think about this morning. Did you check the weather? The forecast is based on statistical models. Did you decide what to wear based on the temperature? You made a decision using data. Statistics is simply the formal way of doing what humans naturally do, making sense of information around us. In this chapter, we're going to build the foundation for everything else we'll learn this semester. We'll start with the basics. What exactly is statistics? Why should we care about it? And how do scientists use statistics to understand human behavior? How many of you have ever looked at your GPA or checked your grade in a class? Here are Chapter 1 learning objectives. To define statistics and explain why it's important to understand. Distinguish between descriptive and inferential statistics, samples and populations, and sample statistics and population parameters. Describe 3 research methods commonly applied in the behavioral sciences: experimental, quasi-experimental, and correlational. State the 4 scales of measurement and identify examples of each. Distinguish between variables that are qualitative or quantitative and discrete or continuous. Let's start by defining exactly what we mean by statistics. Statistics is a branch of mathematics, but don't let that scare you or frighten you. It's really about making sense of numbers and observations. Think of statistics as a toolkit. When scientists observe the world, whether they're studying how people learn, how communities function, or how our health changes over time, they collect lots of information. Statistics gives them the tools to organize that information and find meaningful patterns. Here's a simple example. Imagine you want to know how good a soccer player is. You could watch every single game and try to remember everything, or you could look at their goals per season. That's using statistics to summarize their performance in a meaningful way. Descriptive statistics are when scientists organize and summarize information so it's meaningful to others. They're using descriptive statistics. It's all about describing what the data looks like: averages, totals, and percentages. Connect Here at Albany State, our institutional research office uses descriptive statistics to report graduation rates, student retention, and enrollment demographics. When you see reports about our university success, those are descriptive statistics at work. Now let's talk about the other major type of statistics: inferential statistics. While descriptive statistics summarize what we see, inferential statistics help us make predictions and draw conclusions. So think about political polls. When a polling company says a candidate has 52% support, they didn't ask everyone in the country. They asked a smaller group and then used inferential statistics to estimate what the whole population thinks. They're inferring something about the larger group based on a small sample. Why study statistics? Here's the thing: statistics are everywhere. Your GPA tells a story about your academic performance. Polls predict election outcomes. Health studies inform what you should eat. If you can understand statistics, you become a critical consumer of all this information. And here's what I really want you to understand. Statistics can be misleading if you do not know how to interpret them. The same data can tell different stories depending on how it's presented. Learning statistics helps you see through misleading claims. Can you think of a time when you heard a statistic that seemed surprising or hard to believe? What made you question it? Before we go further, let's get our terminology straight. You'll hear me use the word data a lot in this course. Data is plural. It refers to a collection of scores or measurements. A single measurement is called a datum, though in everyday language, people often use data for both. Research always starts with a question or a statement that needs to be tested. To test it, researchers make observations and record them as numbers. These become our data. Let me walk you through an example from the textbook that illustrates how research works. Suppose researchers want to know if adding sugar to sour tasting grapefruit juice makes people drink it more. This is a health related question. Grapefruit is healthy, but many people do not like the sour taste. So to test this, the researchers would 1. Find participants who dislike plain grapefruit juice. Create 2 groups. One gets plain grapefruit juice, one gets grapefruit juice with sugar. And then measure how much each group drinks. If adding sugar increases intake, we'd expect the group with sugar to drink more milliliters of juice. Notice how we turn a general question into something we can measure with numbers. So let's dive deeper into descriptive statistics. Remember, descriptive statistics are procedures used to summarize, organize, and make sense of data. They're typically presented graphically, in charts, in tables, or as summary statistics like averages. Going back to our grapefruit example, imagine we measured how many milliliters of juice each of the 50 participants drank. We could list all 50 measurements, but that would be overwhelming and hard to interpret. Instead, we use descriptive statistics to summarize. We might calculate the average, the mean, intake for each group. We might create a bar graph showing the difference between groups. We might put the results in a table. All of these are descriptive statistics. They describe what we have observed. Descriptive statistics make raw data meaningful. Without them, we'd be lost in a sea of individual numbers with no way to see the bigger picture. Think about your transcript. Your GPA is a descriptive statistic. It summarizes your academic performance across all of your courses into a single meaningful number. Without the GPA, you'd have to look at every grade individually to get a sense of how you are doing overall. Now let's talk about inferential statistics and why they're so powerful. Inferential statistics allow researchers to make generalizations beyond just the people they actually studied. First, we need to understand what a population is. In statistics, a population isn't just people. It's the entire group you're interested in studying. It could be all college students in the U.S., all residents of Georgia, or all people who dislike grapefruit juice. The population is whatever group you want to make conclusions about. A population parameter is a characteristic that describes that entire population. Here's the problem. You almost never have access to the entire population. You can't ask every person in America their opinion. You can't measure the health outcomes of every patient. So what do you do? Since we can't access the whole population, we select a sample, a smaller group from the population. Then we study that sample and use inferential statistics to make educated guesses about the larger population. A sample statistic is a characteristic of the sample, and we use it to estimate what the population parameter might be. This is the heart of inferential statistics. So let me give you an example you can relate to. Suppose your college newspaper claims that the average college student plays 2 hours of video games per week. To verify this for your school, you could randomly approach 20 fellow students and ask them. You find that the average in your sample is 1 hour per week. In this example, the population is all college students at your school. The population parameter is the average gaming time for all of those students, 2 hours according to the claim. Your sample is the 20 students you asked. The sample statistic is the average you calculate from those 20 students, 1 hour. The goal of inferential statistics is to determine how confident we can be that our sample statistic reflects the true population parameter. So if we want to know the average GPA of all Albany State students, but we only survey 100 students, which is the population and which is the sample? All ASU students equal the population, and 100 surveyed students equal the sample. Now we're moving into how scientists actually collect data. This is where research methods come in. Understanding research methods is essential because the method you choose determines what conclusions you can draw. Science isn't just about collecting data, it's about following specific rules and procedures. Think of it like a game. Without rules, the game has no meaning. Without proper research methods, our scientific conclusions have no validity. The textbook shares an interesting story from psychologist Edward Thorndike in 1898. He observed that thousands of dogs get lost and no one notices. But when one dog finds its way home from far away, it becomes a famous story. Thorndike wondered, are animals actually smart, or do we just remember the unusual cases? And this is why we need scientific methods, to move beyond anecdotes and casual observations to systematic, reliable knowledge. In behavioral science, we commonly use 3 research methods: experimental, quasi-experimental, and correlation. The experimental method is the gold standard in research because it's the only method that you can establish cause and effect. If you want to prove that one thing causes another, you need an experiment. Think about it this way. If I observe that people who drink coffee tend to be more productive, does that mean coffee causes productivity? Not necessarily. Maybe productive people just happen to like coffee. Maybe there's something else going on entirely. To demonstrate cause, we need to control the conditions. We need to eliminate all other possible explanations. And that's what experiments do. So let me give you an example from the textbook. Researchers want to know if writing key terms in bold helps students remember them better. To test this, they selected students at similar reading levels. One group read a passage with 10 key terms in bold. Another group read the same passage with those terms in regular font. Both groups then wrote down as many key terms as they could remember. By controlling everything except the bolding, the researchers could determine if bolding specifically caused better recall. This is directly relevant to your studying. Research like this helps us know which study strategies actually work. The key terms in your textbook are bolded for a reason. Experiments show it helps. For a study to be a true experiment, it must satisfy 3 requirements. If even one is missing, it's not an experiment, and you cannot claim cause and effect. Let me walk you through each one. Manipulation means that researcher controls what's happening to the participants. In our bolding example, the researcher decided which group got bolded text and which got regular text. The researcher manipulated the font size. Randomization means participants have an equal chance of being in either group. You can't let people choose. If motivated students all picked the bold group, we wouldn't know if better recall was due to bolding or motivation. Comparison and control means we need at least 2 groups to compare. Without a comparison group, we have no way to know if the treatment made a difference. These 3 requirements ensure that any difference we observe is due to our manipulation, not some other factor. You can remember MRC: manipulation, randomization, comparison. If you're missing any one of these, you cannot establish cause and effect. Now let's talk about variables. In an experiment, we have different types of variables, and understanding them is crucial. The independent variable, often called the IV, is what the researcher manipulates. It's independent because the researcher controls it independently of everything else. In our bolding study, the independent variable was the font type, bold or regular. The levels of the independent variable are the different conditions. In our example, there were 2 levels, bold and regular. An experiment might have more levels. For instance, we could add a 3rd group with italicized text. Random assignment is how we met the randomization requirement. One simple method for randomization is to put all participant names in a bowl. Draw half for group A and half for group B. This way, any differences between groups are due to chance alone. Why does random assignment matter so much? It ensures that characteristics like intelligence, motivation, and reading ability are roughly equal between groups. Then, if we see a difference in the outcome, we can attribute it to our manipulation, not to differences that existed before the experiment. Now let's talk about the dependent variable, the DV. While the independent variable is what we manipulate, the dependent variable is what we measure. It depends on the independent variable. In the bolding experiment, the dependent variable was memory recall, specifically how many key terms participants correctly remembered. We expect this number to depend on whether they read the bold or the regular text. Here's an important concept: operational definition. How exactly do we measure memory? Memory is an abstract concept, so we can't directly observe it. So what we have to do is to define it in terms of something we can observe and measure. In this study, memory was operationally defined as the number of key terms correctly listed after reading a passage. That's specific and measurable. Different researchers might operationally define memory differently. For instance, by measuring how quickly someone recognizes terms or how accurately they can describe concepts. Operational definitions are essential because they let other researchers replicate your study. If I just say I measured memory, that's vague. But if I say I counted how many of the 10 target words participants wrote down within 1 minute, anyone can repeat that procedure. Not all research can meet all 3 experimental requirements. When a study looks like an experiment but is missing 1 or more requirements, we call it a quasi-experiment. So let me give you an example. Suppose we want to test whether college graduates value education more than people who didn't attend college. We recruit participants and divide them into 2 groups: those who attended college, group college, and those who didn't, group no college. Everyone completes a survey about how much they value education. This looks like an experiment. We have 2 groups. We're comparing them. But there's a critical problem. We didn't randomly assign anyone to groups. People choose whether to go to college long before our study. The variable, college attendance, is pre-existing. Without random assignment, we cannot establish cause and effect. Maybe people who already valued education choose to attend college rather than college causing them to value education. We simply can't tell. So a study becomes quasi-experiment when it 1. Lacks random assignment, 2. Includes a pre-existing variable, one that wasn't manipulated, and or 3. Does not include a comparison or control group. Much of the research in sociology uses quasi-experimental designs. We often cannot randomly assign people to social conditions. We can't randomly assign people to be poor or wealthy, black or white, male or female. So we compare existing groups and draw careful conclusions. In quasi-experiments, instead of an independent variable, we have what is called a quasi-independent variable, also known as a factor. A quasi-independent variable is inherent to the participant, something that exists before the study. So common examples are sex, age, race, ethnicity, socioeconomic status, and education level. These are not characteristics you can randomly assign. For example, if we're comparing multitasking ability between men and women, sex is our quasi-independent variable. It has 2 levels, male and female. We cannot randomly assign people to be male or female. They already are what they are. Another way an experiment becomes quasi-experimental is when there's only 1 group with no comparison. If you test whether a new teaching method improves test scores, but have no control group using the traditional method, you have a quasi-experiment. You cannot know if improvement was due to the new method or something else entirely. The key takeaway, quasi-experiments, can show relationships and patterns, but they cannot establish cause and effect. We must be careful about the conclusions we draw. The third research method is the correlational method. This is different from both experiments and quasi-experiments because we're not comparing groups at all. Instead, we're measuring how 2 or more variables relate to each other. So here's an example. Suppose we want to know if computer use is related to exercise. We measure how many hours per week each participant uses a computer and how many minutes per week they exercise. Then we look at whether these 2 measurements are related. If we find that people who use computers more tend to exercise less, we found a correlation, a relationship between the variables. As one goes up, the other goes down. Here's a critical warning. Correlation does not equal causation. Just because two things are related doesn't mean one causes the other. Maybe people who don't like exercise happen to spend more time on computers. Maybe there's a third factor, like having a sedentary job, that affects both. The correlational method is useful for discovering relationships that might be worth investigating, making predictions based on one variable, and studying things we cannot ethically or practically manipulate. But remember, only experiments with all three requirements can establish cause and effect. Here's a classic example of a famous correlation between ice cream sales and drowning deaths. Both increase in the summer. Does ice cream cause drowning? Of course not. A third variable, hot weather, causes both. This is why we say correlation does not imply causation. Now we're shifting to an important topic, how we measure things. Not all numbers are created equal in research. The scale of measurement you use determines what statistical analysis are appropriate. In the 1940s, Harvard psychologist S.S. Stevens identified four scales of measurement: nominal, ordinal, interval, and ratio. We'll go through each one. To understand these scales, think about three questions you can ask about any measure. Does order matter? Is 2 greater than 1? Are differences meaningful? Is the gap between 1 and 2 the same as the gap between 2 and 3? Are ratios meaningful? Is 4 twice as much as 2? Different scales allow us to answer different combinations of these questions. The nominal scale is the simplest and least informative. On a nominal scale, numbers are just labels. They identify things but do not provide any other information. Think about jersey numbers in sports. If a basketball player wears number 22, does that mean they're better than the player wearing number 23? No. The numbers are just identifiers. Other examples or nominal scales include zip codes, identify location, but 30601 isn't more than 30600. License plate numbers, social security numbers, and phone numbers. In research, we often use nominal scales to categorize participants. Gender, race, marital status, and college majors are all nominal variables. We might code them as numbers for statistical software. Men equals 1, women equals 2. But those numbers are arbitrary labels. The key thing to remember with nominal scales, you cannot do mathematical operations like adding or averaging. What's the average of a Democrat and a Republican? Well, that's just meaningless. Is your student ID number on a nominal scale? Yes, it is. It identifies you, but higher numbers do not mean anything special. Ordinal scales are one step up from nominal. With ordinal scales, the numbers tell us about order or rank. We know that first place is better than second place, and second is better than third. However, ordinal scales do not tell us how much better. In a race, the difference between first and second place could be a fraction of a second or minutes. The rank doesn't tell us. Think about college rankings. The U.S. News and World Report might rank Stanford as 1 and Harvard as 3 for psychology programs. We know Stanford is ranked higher, but the rankings don't tell us how much better. Maybe Stanford and Harvard are nearly identical, while the school ranked 10th is far below both. Other examples: class rank, freshman, sophomore, junior, senior, education level, high school, bachelor's, master's, doctorate, finishing place in a competition. With ordinal scales, you can say one thing is more or less, but you cannot meaningfully add or subtract. The difference between first and second isn't necessarily the same as between second and third. Interval scales give us even more information. With an interval scale, the distance between values are equal and meaningful. The difference between 1 and 2 is the same as the difference between 2 and 3. The classic example is temperature in Fahrenheit or Celsius. The difference between 50 degrees and 60 degrees is the same as between 70 degrees and 80 degrees, 10 degrees either way. This makes subtraction meaningful. We can say 80 degrees is 10 degrees warmer than 70 degrees. However, interval scales do not have a true zero. 0 degrees Fahrenheit does not mean no temperature. It's just an arbitrary point on the scale. Because of this, the ratios aren't meaningful. 80 degrees Fahrenheit is not twice as hot as 40 degrees Fahrenheit. In behavioral sciences, rating scales are commonly treated as interval measures. If you rate your satisfaction from 1 to 7, we assume the distance between 1 and 2 equals the distance between 6 and 7. This assumption is somewhat controversial. Can we really be sure the psychological distance between slightly satisfied and moderately satisfied equals the distance between satisfied and very satisfied? Despite this debate, researchers often treat rating scales as interval data because it allows for more powerful statistical analysis. So think about a 1 to 10 pain scale at the doctor's office. Is the difference between 2 and 3 really the same as the difference between 8 and 9? This is why some researchers debate whether rating scales are truly intervals. Ratio scales are the gold standard, the most informative scale of measurement. Like interval scales, they have equal intervals. But unlike interval scales, they have a true 0 point. When 0 means nothing, ratios become meaningful. If you have $0, you have no money. If you weigh 0 pounds, you have no weight. This allows us to make ratio statements. $100 is twice as much as $50. 200 pounds is twice as heavy as 100 pounds. Common examples of ratio scales include weight, height, age, time, distance, number of eras, number of items recalled, and amount of money. Researchers often prefer ratio scales because they allow the full range of mathematical operations. We can add, subtract, multiply, divide, and make meaningful ratio comparisons. In behavioral research, when measuring memory, researchers might count the number of words recalled, ratio scale, rather than asking, how good is your memory on a scale of 1 to 10, an interval scale. The ratio scale gives us more information to work with. Beyond scales of measurement, researchers also classify variables by whether they are continuous or discrete and whether they are quantitative or qualitative. We've covered scales of measurement, and now let's look at another way to classify variables. This classification helps us understand what kind of data we're working with and what analysis are appropriate. So there are two key distinctions. First, is the variable continuous or discrete? Second, is it quantitative or qualitative? So let's look at each of these distinctions. Continuous variables can take on any value within a range, including decimals. Think about time. You can measure it to seconds, milliseconds, microseconds, and beyond. The precision is limited only by your measuring instrument. Olympic sprinters are timed to the hundredths of a second. If judges wanted to, they could time to thousandths or smaller units. That is a continuous variable. Other continuous variables include height, weight, temperature, the amount of time to complete a task, and the size of a reward in grams. Discrete variables, on the other hand, can only take on specific separate values, usually whole numbers or categories. You can't have 2.5 siblings or attend 1.7 classes. Examples of discrete variables include number of students in a class, number of children in a family, number of errors on a test, body type categories. So here's a good test. Ask yourself, does a fractional answer make sense? If you can have 2.5 hours of study time, it's continuous. But you can't have 2.5 siblings. It's discrete. Is your GPA continuous or discrete? Well, it's continuous. You can have a 3.45 or a 3.456. What about your letter grade? It is discrete. It's an A, B, C, D, or F. Those are distinct categories. Now let's look at the quantitative versus qualitative distinction. Quantitative variables tell us how much or how many. They are measured numerically. Both continuous and discrete variables can be quantitative. Food intake in calories, continuous. Number of items purchased, discrete, or both quantitative. They both tell us about amounts. Qualitative variables, in contrast, tell us about qualities or categories. They describe what type or what kind. They are usually discrete. Examples of qualitative variables include your class year, a junior, sophomore, a freshman, or senior, a type of depression, seasonal, affective disorder, or postpartum or major, a type of book, softcover, hardcover, body type, healthy, overweight, or obese. Here's an important point. Most statistical texts in this book are designed for quantitative variables measured on ordinal, interval, or ratio scales. Qualitative variables on nominal scales have more limited analytical options. That's why in research we often try to operationalize variables as quantitative when possible. Instead of asking, "Are you depressed?" qualitative, we might administer a depression inventory that gives us a numeric score, quantitative. The distinctions we've learned today, scales of measurement, continuous versus discrete, quantitative versus qualitative, will be important throughout this course. They determine which statistical analyses are appropriate for your data. Today, we covered the foundation for everything else we'll learn this semester. So let me summarize the key points. Statistics is the branch of mathematics that helps us summarize, analyze, and interpret data. It is everywhere in our lives. Descriptive statistics summarize and describe data, while inferential statistics help us make conclusions about populations based on samples. We use samples because we rarely have access to entire populations. The three research methods, experimental, quasi-experimental, and correlational, each serve different purposes. Only true experiments can establish cause and effect. The four scales of measurement, nominal, ordinal, interval, and ratio, determine what mathematical operations are appropriate. Variables can be continuous or discrete and qualitative or quantitative. Looking ahead, we'll build on these concepts by learning how to summarize data using frequency distributions, one of the most fundamental descriptive statistics tools. Remember, this is foundational material that everything else builds upon, so now is the time to make sure you understand it.